Okay, let's begin our journey into the world of respiratory physiology. I will warn you that it's not easy, and you really need to take it slow and work on small topics at a time. Some of these concepts are going to require you to understand what's known as gas laws. So, gas laws are going to help us understand certain aspects of respiratory physiology. And in the beginning of this video, I'm going to introduce these three gas laws, and we'll probably refer back to these a number of times. So the first gas law is called Boyle's Law. And Boyle's Law describes the relationship between volume of a container and pressure inside that container. So pressure and volume are inversely related. Okay, so what that means is if you were to make a container smaller, the pressure will go up. If you make that container larger, the pressure goes down. Okay, so that's an inverse relationship. Now, this is showing a syringe. It's a kind of a good example of Boyle's Law. So when you have a syringe and you have a certain volume inside that syringe, right, shown here, if you were to make that volume smaller by pushing the plunger, the pressure inside that syringe goes up, and therefore it will inject the solution. All right, so that's an application of Boyle's Law. What we want to do is apply it to the process by which air is going to move into the lungs, and then how is that air going to move back out of the lungs. Okay, so before I read these descriptions, let's look at this picture. So this picture is kind of a schematic of your lungs, okay, and kind of showing a single kind of blown up alveolus here, and then how it's connected out to the atmosphere. All right, so obviously during inhalation, we want to move air from the atmosphere into the lungs. But in order to move air, you have to have a pressure difference. All right, so air is a lot like blood. If you remember from blood, blood moves from high pressure to low pressure. Well, so does air. So if you want to move air into the lungs, the pressure inside your lungs has to be below atmospheric pressure. All right, so atmospheric pressure is 760 millimeters mercury. So that's largely due to the nitrogen, but that's a mixture of gases in our atmosphere: nitrogen, oxygen, carbon dioxide. Well, all those gases produce a certain total pressure, and that's 760. So how are we going to get air to enter the lungs? Well, we have to somehow decrease the pressure inside of the lungs. And we do that by increasing the size of the lungs. Okay, so there's that inverse relationship. If you can increase the volume of the lungs, you can lower the pressure, and therefore you can have air move from the atmosphere, where it's high, into the lungs, where it's low. Okay, now the inverse occurs during exhalation. During exhalation, we want the pressure in the lungs to be greater so we can move the air back out to the, in this case now, lower pressure. And how do we do that? We decrease the size of the lungs. That will increase the pressure and move that air out. All right. Okay, so now let's read the description. So this is how Boyle's Law applies to the respiratory system. During the process of inhalation, the diaphragm will contract and move downward, and the external intercostals raise the ribs. Now, we'll review this when we get to respiratory muscles, but this drawing shows that. So here's the diaphragm. It's going to drop. That's going to make the chest larger. Here's the external intercostals. They're pulling these ribs out and up, and that's going to make the chest larger. So respiratory muscles, these muscles are going to contract to increase the volume of the thoracic cavity. Whatever the thoracic cavity does, your lungs will do. All right, so your lungs are actually sticking to the inside of the thoracic cavity. There's a surface tension there that allows the lungs to stick to that cavity. So when you make the cavity larger, you will make the lungs larger. When you make those lungs larger, the pressure inside the alveoli go down and air moves into the alveoli. Looking over here during exhalation, these muscles are going to relax. So the diaphragm relaxes, the external intercostals relax. You get recoiling, so the chest gets smaller. And when the chest gets smaller, that's going to raise the pressure inside the alveoli. And now that's going to help move air out of the lungs into the atmosphere. Okay? So Boyle's law, inverse relationship between volume and pressure. That's going to cause changes in the pressure in the lungs relative to the atmosphere and allow us to move air. The next gas law is called Dalton's law. Dalton's law we often refer to as the law of partial pressure. So what that means is when you have a mixture of gases, all right, so the atmosphere is a mixture of gases. There's 79% nitrogen, 21% oxygen, and 0.04% carbon dioxide. So those are the gases that make up that 760 millimeters total atmospheric pressure. Well, they each have what we call a partial pressure. So if you take these percentages and multiply it by the total, you'll get each gas's very own pressure, okay? So each gas has its own pressure, okay? That's called the law of partial pressure, okay? Now, why is this important? How do we apply this? Well, when we're looking at diffusion, okay, so notice down here, at some point we're going to have air inside of our lungs, right? And in that air in our lungs, the oxygen is going to have a certain pressure, okay? Well, the only way to get that oxygen to diffuse into your blood is there's got to be a high to low pressure gradient, all right? For carbon dioxide to diffuse out of the deoxygenated blood into your lungs, there has to be a high to low pressure. So the only way to understand gas exchange is to know that each gas has its very own pressure, okay? And we call that partial pressure, okay? So again, we'll refer back to Dalton's law when we get to this process, but at least now this gas law has been introduced. The third gas law is called Henry's law. I'm not going to really talk that much about this. It has to do with solubility of a gas. So how much gas that gets soluble in a liquid depends on pressure, as well as each gas has a certain solubility. All right, some gases will dissolve in liquid easier than other gases. All right, and kind of a day-to-day example of this is when you open up a soda and you get that carbon dioxide released. That's because you're getting rid of the pressure. All right, so when that bottle of soda has pressure, carbon dioxide dissolves in the solution. Well, when you remove that pressure, it comes out of solution. All right. Now, why is it important for the respiratory system? Well, really, the only part I'm going to use Henry's law for is when we get to the fact that you actually have more carbon dioxide that dissolves in blood plasma than carbon dioxide. And that's because carbon dioxide's solubility coefficient is greater than oxygen's. So carbon dioxide is about 24 times more soluble in a liquid than oxygen is. All right. But again, when we get to that concept later on, I will refer you back to this gas law known as Henry's law. Okay. Change of subject. Let's talk about muscles. All right. So what we're learning about here is how we use muscles to change the size of the thoracic cavity. Now remember, As long as you can change the size of the thoracic cavity, you can change the size of the lungs. All right, so as the cavity gets bigger, the lungs get bigger. As the cavity gets smaller, the lungs get smaller. Okay, so the process of breathing utilizes skeletal muscles, and we refer to this as pulmonary ventilation. All right, so this is a drawing just showing where some of these muscles are. You might remember your diaphragm being kind of a dome-shaped muscle that separates the thoracic cavity from the abdominal cavity. You might remember your intercostal muscles and the fact that you've got externals as well as internal intercostals. You probably remember your abdominal muscles. They play a role in forced breathing. So we're trying to categorize these muscles as, do they contract during inhalation? Do they contract during exhalation? Are they used when you normally breathe, or are they used when you forcefully breathe? So we got two kind of types of breathing. You have what we call normal quiet breathing, so that's what you do at rest. And then you have forced or labored breathing. That's if you're exercising and you really need to exchange a larger volume of air. So when you're normally breathing, the diaphragm and external intercostals contract when you inhale and they relax when you exhale. So exhalation is what we call passive, meaning it doesn't require any muscle contraction. It just requires these two muscles to relax. So when you inhale, the diaphragm flattens, it goes down, and the ribs move up and out. Okay, so the diaphragm lowers kind of the floor of the thoracic cavity, and the external intercostals kind of raise the roof, if you will, or pull the wall up and out. So together that makes the chest larger. And then when you exhale, these muscles relax and that chest gets smaller. Okay, so that's during normal quiet breathing. Now when you start to breathe heavily, you're still going to use your diaphragm and external intercostals during inhalation, but you're also going to use sternocleidomastoid and scalenes. So those muscles are actually in your neck, and they're just pulling those ribs up even more. This upper part of your thoracic cavity can get pulled up even more. All right, so they're used when you forcefully inhale. When you forcefully exhale, you're going to get all these muscles in blue relaxed, right? Because they contracted during inhalation. They're going to relax during exhalation. But then you're going to actually contract some muscles. You're going to contract your internal intercostals, which kind of compress or depress the ribs in and down. And then your abdominal muscles actually push your diaphragm up even more. So that's really going to get that thoracic cavity smaller so you can keep exhaling more volume. All right. I have another slide that I think simplifies this a little bit into the muscles that are involved in normal quiet and then what you add to that. All right. So labored or forced breathing, you're still utilizing the muscles that you do when you're quietly breathing. You're just adding to that. You're contracting sternocleidomastoid and scalenes during forced inhalation, and you're contracting the internal intercostals and abdominal muscles during forced exhalation. So I don't know, this kind of diagram might simplify things a little bit. Okay, next thing, we're kind of going back to this idea of pressure. All right, and I'm going to remind you of Boyle's law. I'm going to remind you that air moves from high pressure to low pressure. Okay, so those are the two things you need to know. So inverse relationship between volume and pressure, and then air moves from high pressure to low pressure. All right, this diagram shows 4 moments during breathing. All right, so it kind of starts at the end of expiration. So let's say you just exhaled, all right, and all of a sudden that air stops moving out. When air stops moving, that means you have an equal pressure inside the alveoli as you do in the atmosphere, and you have no net movement. Okay, so this diagram shows 760 in the atmosphere. That's never going to change, right? Because you're not changing altitudes, you're not changing the pressure that surrounds you. Okay, you can only change the pressure inside the lungs. So at this moment, we have no air movement because the pressure in the lungs is the same as pressure in the atmosphere. Then we're going to start to make that thoracic cavity larger. Diaphragm flattens, external intercostals pull the ribs up and out. Size of the lungs and the size of the alveoli get bigger. And as they get bigger, the pressure goes down. So this diagram shows 759. Now, as you're getting this lung size bigger, you're also adding more gas to it. So as that pressure wants to drop, you're adding more gas, so it's not going to drop very low. We just need to always keep it lower than the 760. So as air enters, you have to keep making those lungs larger if you want that air to continue to enter the lungs. Okay? Then all of a sudden, they equal each other again. Okay? Because you made that lung larger, but you also added a bunch of air in there. And now they're equal again. So at the end of inspiration or inhalation, the pressures equal each other again. Then you begin to exhale, and your chest gets smaller. And as that chest gets smaller, the size of the lungs gets smaller, and the pressure goes up. But as that pressure goes up, air is moving out, so you have to keep making that lung smaller and smaller to keep that pressure inside the lungs greater than the pressure in the atmosphere. All right? And as long as you have a higher pressure inside the lungs, you will move that air out into the atmosphere. Okay? So walk through this. You can read these descriptions on your own. But again, to understand this concept, you have to understand Boyle's law, inverse relationship between volume and pressure, and the fact that air is going to move from high pressure to low pressure. Okay? There's another diagram that's very similar to this. This was actually from a previous book. The numbers are a little different, but this adds one very important concept to this process, and that is that there's a pressure in another location we got to look at. It's the pressure in the intrapleural cavity, or the pleural cavity. So remember, that's that space in between the lung and the chest. There's a little cavity there. And the rule states this: you have to always keep that intrapleural pressure below the alveolar pressure. In no instance can you have the pressure surrounding that lung greater than the pressure inside of the lung, because it would push into that lung and collapse the lung. So notice in every single case here, this is where no air is moving, so alveolar pressure is 760, intrapleural's below it, 756. Then all of a sudden the pressure in the alveoli go down. Well, you better lower the pressure around that lung. All right, then the pressure in the lung goes up. Well, okay, you can raise that intrapleural pressure a little bit. All right, but in every single situation, the pressure in the intrapleural cavity is below the pressure in the lungs. Okay, and that'll make sure that that lung doesn't collapse inward. Now, if you were to puncture the wall of the chest, okay, so let's say for some reason you have some sort of trauma to the chest wall, and it makes an opening between the pleural cavity and the atmosphere. Well, air will want to go into that cavity, all right, because the air in the atmosphere, notice it's 760, the pressure in the intrapleural space is 750 or 754. Air is going to want to go in there if you let it. And if you let air in that little space, it's going to raise this pressure to 760. And that would then cause it to be above the pressure in the lung, and that lung would collapse. There's a name associated with this process, and it's called pneumothorax. Pneumo means air, thorax means chest. So if you cause any trauma to the wall of the chest, you could let air into the pleural cavity. And when air enters that pleural cavity, the pressure goes up and it collapses the lung. All right, so we often call this a collapsed lung, but it can be caused by pneumothorax. All right, so that's a very important additional area that we need to know the pressure. All right, so that's probably a good place to stop. That's a lot of information. So work on that information, process that a little bit, and then we're going to move on to what we call lung volumes and lung capacities.